Hello everybody, welcome back. In this tutorial, we're going to be covering quiz number 24, which is the stresses in pipes. So as you guys will see, typically in these stress-strain type of questions, we either give you the stress tensor or the strain tensor. Now in reality, that's a little bit difficult because we don't really know the stress or the strain tensor. So the goal of this quiz is to give you guys a more realistic scenario. And from there, we want you guys to take realistic things and determine the stress tensor. And the simplest form of this is pipes or tanks. Because in a pipe or a tank, it's very easy to visualize what's going on. And of course, one of the things that we often do know inside of these pipes or tanks is that internal pressure. So that's what we're going to see in this quiz. Instead of giving you guys the stress tensor, we're going to give you the internal pressure in a pipe. And from there, you guys are going to have to determine the stress tensor. So with that being said, let's jump into the theory. So as I was saying, in a realistic problem, chances are we're not going to be given the stress tensor. That's something we're going to have to determine for ourselves. And when we go to pipe or tank questions, this is exactly the case because instead of the stress tensor, we are typically given the internal pressure of the pipe or the tank. Now the question becomes, all right, well, if I know this internal pressure, how can I find that stress tensor? Because once I have that stress tensor, everything opens up. I can find the strains, I can find the von Mises stress, everything like that. But without that stress tensor, I don't have no idea what to do. So the answer to this is it depends on the condition that we're given. And when we're dealing with these pipes or tank questions, we're going to examine two conditions. Condition number one, which is on the left here, has capped ends. So this is the case of a tank. Think of a propane tank, something like that, where it has those capped ends. Now this is important because that pressure that's going laterally will cause it to expand in that E1 direction. So that's going to be the key here for condition one. And it's actually the easier of the two conditions, even though it looks a little bit more difficult. Now condition two is what we call restrained ends. So this restricts any movement in the E1 direction. An example of this would be a big, large-scale pipeline that goes for hundreds of kilometers, something like that. Now, in this condition, it's a little bit more challenging, but we have to use the identity that it cannot expand in that E1 direction to help us determine some of the stresses. So let's jump into what the stresses for these two conditions would be. So condition one, which I call capped ends, the pipe is allowed to expand in all three directions. There's no problem at all. It's just basically a simple tank. So from there, what we can do is we can actually say that our stress tensor, sigma, is going to look as follows, where we have a sigma 1,1, a sigma 2,2, and the rest are all zeros. So this becomes really nice because we say, all right, well, if I know these sigma 1,1, sigma 2,2, I have my stress tensor. And if I have my stress tensor, well, the rest is pretty easy. So the question becomes, how do I calculate this? Well, the nice thing about these pipes is it follows a simple formula where the stress is simply going to be the force divided by the area. So with that, I can simplify sigma 1,1 and sigma 2,2 into the quantities that I do know. So sigma 1,1 is actually going to be the pressure P multiplied by the radius R, all divided by 2 times T, where T is that wall thickness. And sigma 2,2 follows almost the identical formula, except we remove that 2. So sigma 2,2 is going to be the pressure times the radius divided by the wall thickness. It's that simple because when we think about a realistic pipe, we know what pressure we're going to have in there because that's something that we determine or design for. We know the radius and the wall thickness of the pipe, so we can very easily determine the stress tensor. Now, what I said in the last slide kind of contradicts this. Remember, I said that we can expand in all three directions in this case. So shouldn't there be a sigma 3,3, a stress in the third direction or the E3 direction? Well, there actually is. So don't think that sigma 3,3 is actually 0. But when we deal with these type of pipes with a large diameter compared to wall thickness, so think of a big oil and gas pipe where we have a diameter of 1 meter, but our wall thickness is only 20 millimeters, something like that. Well, there is a sigma 3,3, but it's negligible compared to sigma 1,1 and sigma 2,2. Therefore, we can neglect it or ignore it, which is great for you guys because if we ignore it, it actually means a lot less work. And as we'll see in the last slide, ignoring it will actually allow us to make a nice assumption. And this assumption will help us with our calculations very nicely. But before we go into that assumption, let's look at condition number 2, which is restrained ends. So with restrained ends, the pipe cannot expand in that E1 direction. So if I'm looking at the stress tensor, which is going to be exactly the same as before, what I'll realize is I cannot calculate sigma 1,1. Sigma 2,2 is going to be fine because it follows the exact same procedure as before. But since the pipe cannot expand in that E1 direction, I don't know what sigma 11 is. So the question is going to be, all right, if I don't know the sigma 11, how can I determine sigma 11? Well, what we're going to have to do is use the identity that if the pipe cannot expand in that E1 direction, it must have no strain in that direction. Therefore, the strain in E11 must be 0. And from there, what I can do is I can look at the formula for strain in the E11 direction. So this comes directly from the 6x6 isotropic linear elastic material matrix. I can say that my strain in the 1,1 direction, or epsilon 1,1, is equal to sigma 1,1 divided by E minus V times sigma 2,2 divided by E minus V times sigma 3,3 divided by E. And this is the most general formula. This can apply for everything that is linear elastic isotropic, which in this case the pipe is. But we also know a couple things. The first one is that sigma 1,1, or sorry, epsilon 1,1, we know it's going to be 0 because it cannot expand. And then we also know that sigma 3,3 is, well, it's not 0, but we assume it's 0 or negligible. So therefore we can cancel out two terms in this formula, and we're left with sigma 1,1 divided by E minus V times sigma 2,2 divided by E. And of course, this will equal 0 because of our epsilon 1,1 is equal to 0. So all I'm going to do is I'm going to move that subtract V times sigma 2,2 divided by E to the other side. What I'll find out is that there's E's on both sides. I can just cancel them out. And I get the identity where sigma 1,1 is simply going to be V, our Poisson's ratio, times sigma 2,2. And after I know sigma 1,1, well, it's very simple. I have my stress tensor. So as we'll see, the main goal of these questions is determining the stress tensor, which from what we've seen is very simple, but then it also asks us to determine the strain tensor. Now, the pipes are a linear elastic isotropic material, and if we know all the stresses, then we can go to that nice 6x6 matrix for linear elastic isotropic materials. However, we can actually save ourselves some time, because if we remember that both of these conditions, sigma 1,3 is equal to sigma 2,3, which is equal to sigma 3,3, which is 0. And you guys may remember, well, this is plane stress. And under plane stress, we can find the strains using a simpler 3x3 matrix instead of going to the big giant 6x6, where epsilon 1,1, epsilon 2,2, and 2 times epsilon 1,3 can be found using the following relationship. If we look at the relationship, everything in the center there, well, that's just a function of V and E, which we're typically given. The Poisson's ratio, well, it's typically steel, so that'll probably be around 0.3. E, again, for steel, maybe 200,000 MPa or 210,000 MPa, something in that ballpark. And then the final thing at the very right is sigma 1,1, sigma 2,2, and sigma 1,2. And we know all those from our stress tensor, so therefore we can find the strains. Now, the one thing that we're going to have to keep in mind with this plane stress assumption is there actually is an epsilon 3,3. It's not going to be determined through the following relationship, but its own separate formula, where epsilon 3,3 is simply the negative Poisson's ratio divided by E multiplied by sigma 1,1 plus sigma 2,2. So again, V and E we already know, and by this stage we also know sigma 1,1 and sigma 2,2. So from the plane stress assumption, we can very simply solve for all of the strains, which is exactly what these questions will want. So that concludes the theory, guys. As you guys may see or may know by now, pipelines or pipes, tanks, not too bad. Very simple to do, very simple to calculate, all because that sigma 3,3 is equal to 0, and we can use plane. So let's jump into the examples where we can actually start to see this in action. Alrighty guys, welcome to the quiz. Now before we begin, I just want to make a little disclaimer that I remodified this quiz a little bit to make it a little bit easier for me to write. So what we're going to have is your guys' quiz is 4 questions. Mine is 2 questions. So as you guys will see, the first question in your quiz is a simple matching question. I anticipate there's going to be no problem with that whatsoever, so I just removed it. You guys know how to match things. I'm not too worried about that. So we're left with questions 2, 3, and 4. Now questions 2 and 3, they're basically the same question as we discussed with pipes, just with those 2 different conditions assumed. So I squished those together into one question, which will be question 2 in my little quiz here. And then finally, question 4 of your quiz, well, that's going to be question number 1 of my quiz, because it's a nice simple question, nice way to kind of get your quiz juices flowing, ready to go. And then we're going to move into questions 2 and 3 in the quiz, which are kind of the meat and potatoes of this quiz. So if we look at question number 1, question number 1 says a linear elastic material with Young's modulus E and Poisson's ratio V is in a state of plane stress. And what I'm going to do is I'm actually going to highlight this because this plane stress assumption will be the key to this question. And it says such that sigma 11 is equal to sigma 22, which is equal to P, while sigma 12, so that shear stress, is equal to 0. And it says determine the value of epsilon 33. Now, the key to this again is going to be that plane stress, and you guys will see why. So if I'm looking at epsilon 33 in the most generic way possible in a linear elastic isotropic material, we can actually calculate epsilon 33 with the following formula. And this formula comes directly from that 6x6 constitutive behavior, or the elasticity tensor, as I often call it. So it's equal to negative V sigma 11 all divided by E. And you guys will know this formula very well by now. Subtract V times sigma 22 all divided by E. And then finally added to sigma 33 all divided by E. Now, if we look at this formula, it has V and E, which we know, or we don't know, but we want it a function of, so the V and E are not a problem. It has sigma 11 and sigma 22, while we know that those are both equal to P. So the question becomes, well, what is going to be that sigma 33? And this is why we have to use that plane stress assumption. Now, here's the key to it, plane stress, because what happens in plane stress, sigma 13 is actually equal to sigma 23, which is equal to sigma 33. And that sigma 33 is the one down below. And we say that these are actually all equal to 0. So in the case of plane stress, sigma 33 is actually equal to 0. So what I can do is I can cancel out this whole term at the end here. Why is that great? Because now I have my epsilon 33 and everything that I want it to be. So epsilon 33, well, this is equal to negative V and then times sigma 11. Well, we know sigma 11 is actually just P, so we're going to have P down here divided by E. And then we have minus V times sigma 22. Oh, wait a second. We know that sigma 22 is just going to be P yet again. And this is divided by E. So what we can do is we can simplify this, and I'll just put a little arrow because this is actually our final answer, where sigma 33 is actually equal to negative 2 times P times V all divided by E. And this is the answer to that question. So it's a nice, simple, easy question. But if we didn't know that we assumed plane stress, it actually becomes impossible to solve because we don't have a value of sigma 33. However, once we use plane stress, well, we know that sigma 33 is simply 0, and we have everything else that we need to solve this question. So that is question number 1, or in your case, question number 4 of this quiz. Now let's jump to questions 2 and 3, which have to deal with the stresses in pipes and basically what you guys are here for. So question 2 of my quiz is basically questions 2 and 3 of your guys' quiz. And what I did is I put that question 2 is actually equal to part A of this question, and question 3 is part B of this question. Because as we look in this pipe, it has the exact same parameters for both questions, so we might as well just include it into one nice question. And it's nice to then compare how it changes based on the conditions. So question number 2 says, the shown idealization is used to model a tank with an average diameter of 0.5 meters and a wall thickness of 20 millimeters. Now, the figure it's referring to is the one that I showed you guys in the theory examples in those slides. However, in your guys' quiz, you guys are also re-shown this figure, so you guys are very well aware of what it looks like. And it says the internal pressure of a fluid inside the tank is 40 MPa. So this 40 MPa that's right here, this is actually that pressure P that we're going to need to calculate our stress tensor. Now it says, consider a point on the wall of the cylinder and assume the coordinate system of the point as shown in the figure. So again, you guys are given that nice little figure. And it says, if the Young's modulus is 210 GPa and the Poisson's ratio is 0.3, so I'm going to highlight those because we're going to need those. It says, determine the stress and the strain tensors of the point under the following conditions. So part A says the tank is 2 meters long with capped ends. So it doesn't explicitly say this, but this is basically condition number 1. So if it has capped ends, the pipe is allowed to freely expand in all 3 directions. But then part B says the tank has restrained ends, which would be condition number 2, which means the pipe is not allowed to expand in that E1 direction. So we know that we're going to have to modify things a little bit to accommodate that. Now I'm going to scroll down a little bit, and we're going to start off with part A right here, which is basically question 2 for you guys. Now, in its simplest form, we know that the stress tensor, or let me try and write that a little bit better. Again, I'm trying not to use the lines anymore to make it look a little bit nicer, but of course, I'm going to make this look a lot worse at the same time. So we know that the stress tensor for our pipes, both in part A and part B, they're going to be the same, where we have sigma 1, 1, 0, and 0. We have 0, sigma 2, 2, 0, and then finally our third column is just going to be straight 0. So a whole lot of nothing going on in that third column, and I'm going to finish it off. So if I look at this stress tensor, all I need is sigma 1, 1 and sigma 2, 2. And of course, these are dependent on the conditions. Well, sigma 1, 1 is. Now, a lot of you guys may be wondering, well, shouldn't there be a sigma 3, 3 down there somewhere? Well, there is a sigma 3, 3, but as we can see from this picture, or I guess the information in this question, we are dealing with a pipe with a very large diameter compared to its wall thickness, so we can say that sigma 3, 3 is approximately 0, or it's negligible. We don't really care about it, and that's really nice because it allows us to use plane stress. Now, the question becomes, all right, well, how do I determine these sigma 1, 1 or sigma 2, 2? So I'm going to come down a bit more and say, all right, well, I know that for condition 1, my sigma 1, 1 is actually very easy to determine in the sense that it's going to be the pressure times R all divided by 2 times the wall thickness. So what I'm going to do is I'm going to come over again and say, all right, well, I know that my pressure was 40 MPa. That comes directly from the question. And my radius is 0.5 meters. Now, this is where students may start having some trouble, is that when we're dealing with these type of analysis, and actually I'm going to write this up in the corner, both now and especially in the future, especially when we get into finite element modeling, we need to make sure that our units are consistent. So what I like to do, and this is what you guys should do too, in my opinion, I'll never tell you guys what to do, but this is my recommendation. We always want our units in 3 things. For pressure, we say MPa. Well, we had 40 MPa, that's good to go. For force, we say newtons. Well, we're not dealing with any force here, so we're fine. And then our dimension of length should be in millimeters. And the reason why is this always makes for a nice conversion. For example, if I want to stress and I have my force in newtons and my area in millimeters squared, well, then I know I'm going to get MPa as an answer. So therefore, it allows us to switch freely between them. So when I look at the radius of this pipe, I have to kind of scroll up to the question. We're not given the radius, or are we given the radius? It says a diameter. So we're not given the radius. We know that the pipe has a diameter of 0.5 meters. So again, we're not interested in that diameter. We're interested in the radius, which will be 0.25 meters. However, we should not input this as meters. We need to input it as millimeters. So what I'm going to do is come down here. Again, I know the radius is 0.25 meters, but that is the same as 250 millimeters. So it's very important that we have that in millimeters, because if we come down below, we multiply 2 by the wall thickness. Well, the wall thickness we were given as simply 20. And if I were to go 0.25 divided by 20, well, of course, my answer is going to be a lot different than if I go 250 divided by 20. All right, so what we do is we just throw that into our calculator, or you guys are brainiacs, so you guys can just do it in your head. And what you guys will find out is that sigma 1, 1 is simply equal to 250 MPa, which is great. We have our first component. We can come down and say, all right, well, how about our second component, sigma 2, 2? Well, it's almost the same formula where we go the pressure times the radius divided by the wall thickness. However, in this case, on the bottom there, we don't have the 2. We just simply have the wall thickness. So we can come over to the side and say, all right, well, this is going to be 40 MPa multiplied by the radius, which is 250. And we can divide by the wall thickness, which is 20. So we know it's going to be the exact same as sigma 1, 1, just multiplied by a factor of 2. So we know that sigma 2, 2 is going to be 500 MPa. And now that I have sigma 1, 1 and sigma 2, 2, if I look up at my stress tensor, I have everything that I need to know in my stress tensor. I can carry on and find the strain. But for you guys, of course, this is one of the questions that it asks for as an answer. So what I'm going to do is I'm going to write my stress tensor in the way that will be inputted into your quiz. So I'm just going to come down, make a line, try and make it as straight as possible. I know I'm not the best at this, but
you guys are fairly nice to me, so I assume that there won't be too much outrage going on. So I got 250, 0, 0. Then I have 0, and then sigma 22 we say is 500, so 500, and then 0. And then finally our last column is simply zeros. So this will be our stress tensor right here. As we can see for pipes, not too bad at all. I don't anticipate you guys having too much problem. And of course, the units of this are going to be MPa. So don't be worried. Sometimes they give you GPa, MPa. We're going to have to make sure that we have it all. But of course, again, my recommendation, always have it in MPa, newtons, and millimeters. It'll make your guys' lives a lot easier. So what I'm going to do is I'm going to scroll down right here, and we're going to start talking about, okay, well, I have the stress tensor. How can I find the strain tensor? So the key to this one is if we look up at our stress tensor, we see that sigma 1,3 is equal to sigma 2,3, which is equal to sigma 3,3, which of course is all equal to 0. Why is this so nice? Well, this means that we have our plane stress. And if we have our plane stress, well, that means that we don't need to go to that 6x6 very gross looking thing. We can actually simplify this into a nice 3x3 expression, a 3x3 matrix expression, which I'm going to write right now. So as we can see, it's a lot nicer looking. And in that matrix in the center, that elasticity tensor, it's simply a 3x3 tensor instead of a 6x6, so that makes our lives a lot easier. Now, if we look inside of this elasticity tensor, we see that we have E in it. We see that we have V sprouted a couple different times, but that's basically it. We only need E and V. So all I'm going to do is say, all right, well, I know that my V, my Poisson's ratio, is 0.3. And my E, well, that's my elastic modulus. We're given as 210 GPa. So I'm going to put GPa here, because if we enter 210 GPa, we're going to have a problem, because that means that we're inputting E as GPa, but our stresses are in MPa. So what we do is we want to convert the 210 GPa into MPa. So this will be 210,000 MPa. And that's what we're going to use to throw into here. And what we do in the end is we just substitute all the numbers. You guys are really good at your calculators. And what we'll find out is that our strain vector here, which I'll put right here, is E11, guess epsilon 11, epsilon 22, and then 2 times epsilon 12. This will be equal to, and I'm just going to finish off the brackets here, make it try to make it look as nice as possible for you guys. All right. So we're dealing with strains, so we expect small numbers. So for epsilon 11, I get 0.000, so 3 zeros to start, and then 476.19. For epsilon 22, I get something a little bit bigger. I get 0.00, so only 2 zeros instead of the 3, and I get 238. So 238. And then finally for epsilon 12, my shear strain, I actually get that is equal to 0. So if I come down here and I say, all right, well, this is perfect, because right now I have epsilon 11, epsilon 22, and then epsilon 12 at the same time. I already know that epsilon 13 and epsilon 23 are going to be equal to 0. So therefore, the only thing I'm really missing in my strain tensor is going to be epsilon 33. So I'm going to just scroll down a little bit here. And I say, all right, well, I know that epsilon 33 under plane stress. So here's the key takeaway again. We're dealing with plane stress. We have a nice simple formula where epsilon 33 is simply negative Poisson's ratio divided by E multiplied by sigma 11 plus sigma 22. And what I'll do is I'll substitute the numbers because it's a little bit simpler than before. So for V, we know that it is 0.3. That's nothing too crazy. For the Young's modulus, again, we want to input it in MPa so that the units are consistent. So we have 210,000. And then sigma 11, well, that was 250. And then sigma 22, well, we know that that is simply 500. So we multiply all those bad boys together. What we get is that the strain is equal to negative 0 point, and what we're going to have is 2 zeros. So 0, 0, and then 1, 0, 7, 0, 7, 1, 4, 2, 8, 1, 4, 2, 8. So that now I have my epsilon 3,3. I also have epsilon 1,1, epsilon 2,2. This question is basically finished, but what we can do is we can simplify it into just kind of one nice strain tensor for you guys, because that's how you guys are going to input it into E-class. So I'll just kind of start off my strain tensor like this. Well, I start off with epsilon 1,1, and I won't put too many significant digits. So we have 3 zeros, and what I'll do is I'll just go 4, 8, because of course you guys can see the actual digits if you guys want to. We found out that epsilon 1, 2, and 1, 3 are equal to 0. Moving on to the second column, our only non-zero is going to be epsilon 2, 2, which was 0.00202. So I'll just go 202. I won't put too much more. Again, you guys can see all the extra decimal spots if you guys want to. And then moving on to our third column, we found out that we do have a non-zero epsilon 3, 3, and that is equal to negative 0.00107. So 107. The other ones were just simply zero values, so I'll end off like this. I'll finish this off, and yes, this tensor looks a little gross because there's so many decimal places, but in the end, this is what you guys get. So in the end, not too bad to do, and the key assumption is using that plane stress. So I'll highlight this again right here. And why is plane stress so sexy for us? Well, if we look down at our tensor below, our elasticity tensor to be more specific, when converting from stresses to strains, we have a 3x3. We don't have to deal with the 6x6. Of course, if this was 6x6, well, let's be honest, we're just going to throw in Mathematica, but it does make for a little bit of extra work. From here, I was just able to throw it into my trusty TI. Not a bad process at all. So we're going to go back up to the question, and we're going to say, all right, well, that was part A. And again, part A dealt with condition number 1, which is capped ends. How about if we look at part B now, which is condition number 2, which is restrained ends. So we're going to come down here, and let's change our color. Let's mix it up a little bit for part B. Let's throw this one in blue, because why not? So I'm going to come down here. We're going to have almost a new page. I'm going to say, all right, well, now we're dealing with part B. The nice thing about between part A and B is that they do have a lot of similarities. So one of the things that we saw in the theory is that sigma 1, 1, we don't know. So what we're going to do in our stress tensor is we're going to have sigma 1, 1 as an unknown. The rest are equal to 0, except for sigma 2, 2. But the nice thing about between these two things is sigma 2, 2 in condition 1 and sigma 2, 2 in condition number 2, they are the exact same. So sigma 2, 2 we calculated for as 500 MPa. I'm just going to leave that as 500 MPa because that does not change. And the rest, of course, are going to be 0. So I'll just finish this off here. I'm going to do this one a little bit faster than before because, of course, it's the exact same process as before. So, of course, since we have sigma 1, 3, sigma 2, 3, and sigma 3, 3 is equal to 0, I'm also going to make a note that we can have our plane stress assumption, which will make things go a lot quicker. So plane stress, not a big deal, but again, the question really becomes, what is going to be that sigma 1, 1? And I'll highlight it in here so we can really show you guys this is what we're missing. We don't know what sigma 1, 1 is. However, what we do know is the strain in the E1 direction, or epsilon 1, 1, is equal to 0. So we know that epsilon 1, 1, which is simply going to be, if we're looking at a general linear elastic isotropic material, is going to be equal to sigma 1, 1 divided by E minus Poisson's ratio sigma 2, 2 all divided by E, and then minus Poisson's ratio sigma 3, 3 all divided by E. And we know that this is all going to be equal to 0 because, again, we're preventing that lateral expansion or contraction. We also know that sigma 3, 3 from above is going to be 0. So what I'm going to do is I can just cancel all of this out. And therefore, I can move stuff to one side. And I'm just going to switch my pen again. I can say that, all right, well, I know that sigma 1, 1 divided by E is going to be equal to the Poisson's ratio sigma 2, 2 all divided by E. I have E on both sides. I can simply cancel it out. Therefore, my sigma 1, 1 is going to be equal to V times sigma 2, 2. Well, I know what V is and I know what sigma 2, 2 is, so my V is simply 0.3, so 0.3, and I multiply that by sigma 2, 2, which I know is 500 MPa. And what I get is that my sigma 1, 1 in this very particular case is equal to 150 MPa. So as we can see, it's less than condition number 1 where we had 250 MPa. But what's nice about this is I can say, all right, well now I know sigma 1,1, I know sigma 2,2. I can come down here and write down my stress tensor in its full form. So we know that sigma is a nice stress tensor, so I'll draw some nice brackets. And we know that sigma 1,1 now is 150, so we go 150. The shears are 0, so come up here 0. Sigma 2,2, we said that's actually the exact same as condition 1, which is 500. And then the remaining are, of course, are all 0. So we'll just end this right here, looking very nice. That's a little bit diagonal, so let's try and make it look a little bit nicer for you guys. I probably made it look worse, but we'll just ignore that. And of course, we have units of MPa. Now what I can do is, now that I have my full stress tensor, I can use the relationship of plane stress to figure out what my strains are. So the plane stress relationship is as follows. And again, I know that my Poisson's ratio V is simply going to be 0.3, and my Young's modulus in this case in MPa is 210,000. So all I have to do is substitute all my values in. I can solve for epsilon 1,1, epsilon 2,2, as well as epsilon 1,2. So I'm going to come down here and say, all right, well, just simply doing the math into my calculator, or again, you guys are probably doing it in your head. You guys are that smart. We have epsilon 1,1, epsilon 2,2, and of course I didn't make this big enough. We have epsilon 1,2 at the very end. Finish off the bracket, and what we do is we get some very nice things over here. So I'm going to come over here, finish it off. So epsilon 1,1, you guys don't really need to do the math, because again, one of the things that we said under this condition is epsilon 1,1 is actually equal to 0, because we prevent that expansion. If you guys do the math though from above, you guys will get the exact same answer, so don't be too worried. Epsilon 2,2, we have 0 point, and then what we have is 2 zeros. So 0, 0, and then 2, 1, 6, 6, 7. And then epsilon 1, 2, so that's shearing strain, same as before where we get it's equal to 0. Finish this off here. And when we say, all right, well, I have all my strains now except for one, which is epsilon 3,3. So I'm just going to scroll down a little bit more. And we know that epsilon 3,3 can be found using the nice formula below, where epsilon 3,3 is simply negative V divided by E, and then times sigma 1,1 plus sigma 2,2. I just substitute my values in, so I know that my V is 0.3, so I go negative 0.3, all divided by my Young's modulus, which is 210,000, and then multiplied by sigma 1,1 plus sigma 2,2. So sigma 1,1 we said is 150 in this case. Sigma 2,2 is still 500. That doesn't change between conditions. And when I throw all of this in, I get that epsilon 3,3 is negative 0. And then 30, so 1, 2, 3, 92857. So 9285, and then 7. Of course, there are more decimals, but I'm just going to stop there. And now that I know all of these strains, I can put it into one simple strain tensor, which I'll try and include at the bottom here. It gets hard writing at the bottom of the iPad. But I'm trying my best for you guys, don't worry. I'll always give you guys my best effort. So if we look at that first column, epsilon 1,1 is 0, same with 1,2 and 1,3. So our first column here is actually just a bunch of big fat zeros, nothing too special going on here. Second column, our only non-zero component is epsilon 2,2. So I'm going to have 0.00217. And again, I'm just cutting off decimals. You guys know that it's a little bit more than that, but you guys can figure that out, no problem. And looking at our third column, the only non-zero component is epsilon 3,3. So I'm going to have negative 0.000, so 3 zeros. And then I'm going to just put 9,3, 9,3, and the rest will be 2 zeros up here. Not bad at all. And I'll finish it off as follows. And that's it. That's quiz number 24. So I hope you guys enjoyed it, or at least learned a little bit of something. The stresses in pipes, not too bad. As you guys see, not too bad. The key assumption that we're using in all three of these questions, so not only the pipe question, but as well as question number 1, and I'll highlight it right here. Plane stress. And that's really nice because it makes our lives a lot easier. Usually when people say, oh, you have to assume something like this, they think, oh God, it's going to make my life a little bit more challenging. Well, in this case, seeing plane stress, you're thinking, perfect. I know that sigma 1, 2, sigma 2, 3, and sigma 3, 3 is 0. Therefore, instead of an ugly 6 by 6 matrix, I can use a simple 3 by 3. Thank you guys so much for listening. I really appreciate it. I will see you guys in quiz number 25.